the double slit experiment, and a tiny arrow that spins while an electron travels. That spinning arrow explains all of quantum mechanics. The setup: a source, a barrier with two slits, and a screen. With bullets, you get two bumps, one behind each slit. More paths, more hits, always. With electrons, stripes, bright, dark. Some spots get hit a lot, others, zero, exactly zero. Wait, stop. The electrons are fired one at a time, one after another. There's only ever a single electron in flight, and yet every single one avoids the dark spots. Not on average, every single electron, as if it already knew where it wasn't allowed to go. The explanation is an arrow that spins. Imagine a clock, a hand that spins at a steady rate. It has a length and it points in a direction. This hand spins while the electron travels. Not in the physical world, in nature's own bookkeeping. And at the end, length squared equals probability. Here's the crucial part that most explanations leave out. As the electron travels, its arrow spins, and it spins in proportion to the distance covered. Watch carefully. The electron moves from left to right, and the hand above spins along with it. The farther the electron travels, the more rotations. Why does it spin? Because each tiny step of the journey contributes a small rotation. That small rotation is proportional to the energy balance along that step. Kinetic energy minus potential energy. The sum of all the small rotations over the entire path is called the action. And the action, divided by Planck's reduced constant h-bar, is the total angle of the arrow. At a bright spot on the screen, the two paths have similar lengths, so the arrows have spun a similar number of times. At the end, both arrows point in nearly the same direction. You chain them end to end, a long total arrow, high probability, bright stripe. At a dark spot, one path is just long enough that its arrow has spun exactly half a turn more. The two arrows point in exactly opposite directions. Chained end to end, they cancel out completely. The total arrow is zero. Zero squared is zero. Not small, not unlikely. Mathematically exactly zero. Not a single electron ever arrives here. Because the amplitude is zero before the electron even makes up its mind. And that's the difference. Classically, you calculate with probabilities, positive numbers that can never cancel out. In quantum mechanics, you calculate with arrows. And arrows pointing in opposite directions add up to zero. Same bookkeeping, different currency. Now the thought that blows everything wide open. Take away the barrier, no slits, free flight from A to B. How many paths are there? Infinitely many. The straight path, a curve to the left, the path that flies to the moon and comes back. Every path gets an arrow. Now look at the straight path. Its hand spins a certain number of times, and a path that lies just a hair's width away? Almost the same length, almost the same spin, almost the same angle. The arrows point in similar directions. They reinforce each other. But a wild, crazy path? It's much longer. Its arrow spins hundreds, thousands of times more. And the neighboring path, just slightly different? It already has a completely different spin count. The arrows point in random directions. Random arrows chained end to end produce a tangled knot. The knot goes nowhere. The crazy paths cancel each other out. What survives is a narrow neighborhood around the classical path. And that is exactly the path a ball, a planet, a bullet takes. Not because nature chooses it, but because it's the only one whose neighbors don't destroy each other. And now it becomes clear why Planck's reduced constant h-bar matters so much. The total angle of the arrow is s divided by h-bar. The smaller h-bar is, the more the arrow spins for a given action. A tennis ball has an action of about 11 joule seconds. Divided by h-bar, that gives 10 to the power of 34 full rotations, 17 billion times around. If the ball deviates by just 1/1,000,000th of a millimeter from the straight path, the arrow already spins 100 billion times more. Neighboring paths point in completely random directions. Everything cancels out. The tennis ball only feels the classical path. An electron in the double slit has far less action, only about 10 to the power of 9 rotations. And its quantum corridor is 3.5 micrometers wide enough to explore both slits. That's why electrons show interference and tennis balls don't. No difference in principle, just a difference in scale. And finally, why does measuring destroy the interference? When you detect which slit the electron goes through, the paths become distinguishable. And the quantum rule is strict. You only add arrows for indistinguishable paths. Distinguishable paths, separate probabilities. Those can't cancel out. No interference, no stripes. It's bookkeeping, not mysticism. What you just saw has a name: Feynman's path integral. The amplitude to get from A to B is the sum over all paths. Each path contributes an arrow whose angle is the action divided by h bar. All of quantum mechanics, in one line. The interactive version, where you can explore everything yourself, is at ki-mathias.de/n/quantum.html.